Good afternoon. Am I audible? Please confirm. Just anyone confirm? One second. Okay, so since I am audible, let me try to, yes, good afternoon. Let me try to share the screen. Okay, okay. Let me share my screen. Before that, let me, okay, sharing the screen, entire screen, BenQ, share. Okay, so hope you are able to see the things and from the beginning. Okay, slide show, slide show, slide show from beginning. Okay, yes, okay, yes. Hope everything is clear. I think so. Voice and everything is clear. Okay, okay. So we know our course is RTL design and Verilog HTL. So yesterday we were looking into the introduction to the VLSI design. Now we will try to understand the VLSI design flow and then the semiconductor industries, what all are involved in that and such kind of things. This is very much important for your career. So that's why we have been kept this as one of the sessions. So you guys will be able to get what is going on in the semiconductor industry, so you will be able to get much insights about it. Okay, so with this let us move into the first slide. Okay, okay, so as we seen in the previous session also about the evolution, little bit somewhat a slight difference. Okay, so first they call it as the is a small scale integration. Only with fewer transistors they were able to integrate the stuffs, and then the medium scale integrations. Okay, so let me remind you guys, today I thought of introducing an online tool, EDA playground. That also, yesterday I told that I will be using Ubuntu 24 and with open source. And then one more thing also, we can go and use an EDA playground, okay, for doing the simulation and purpose also. So at the end of the thing, let me introduce to that also. Okay, uh, first they were using the first type of the starting was something small scale integration. Then they went and integrated hundreds of transistors, and then they went for thousands, then millions to billions. Now they are it is something in an advanced modern chip. They were using ultra large scale integrations. Okay, so these are some evolutions in the VLSI. So now we will try to understand the semiconductor industries, because this is very much important for you guys. Okay, when it comes to the career perspective, this knowledge you must need something. So if you able to have an higher view or have an overview of the this idea, you will know what you are working and how you will be able to do the things. Those things you will be able to understand it. Okay, so the semiconductor uh, industry consists of multiple business models and technology domain. This is what you have to understand. This first line you have to understand it. Okay, it is not like that. It is having only one business with it. Multiple of many companies, they will come together. See, to make one chip, it is not with only a single company. Many business, multiple business models were been involved, and multiple technologies were involved in it. Okay, so that you have to understand. So in the industry segments, you can see that fabrication, fabless means fabrication less. We might be thinking the companies who are involved in semiconductor company, they will provide the chip. No, there are companies which they will provide only. They will only design the chip, and they will give it to other company for the manufacturing. Okay, so that kind of companies, let us check fabless companies. What they are telling, it will design chips but outsource the manufacturing. So these companies will not manufacturing the chip by themselves. They will outsource they will go and do only the design part. Okay. For example, Qualcomm, Nvidia, AMD, MediaTek, Broadcom, these are the companies, they will do their design. Please understand, the design of the chip is done by these companies, but they will outsource for the manufacturers. That is what the thing. Next, foundries, what they will do, they will manufacture the semiconductor chips like TSMC, Samsung Foundry, Global Foundries, UMC, SMIC. These all are the companies where they will manufacture the semiconductor chips, which already the previous companies know that they have done the design. From the design, they will be able to do this stuff. Okay, that is the idea. Next, integrated device manufacturing. What is this? There is a design also, there is a manufacture also, and they will do sometimes package chips also. Okay, so if you consider the Intel, they will do their design, they will manufacture us, and they will do different for the same manufacturing chip. They will have different kinds of packages, so they are able to do all. Okay, that is what integrated device manufacturer. So Intel, Texas Instrument, Micron, Infineon, ST Microelectronics, all other things are something like this. Okay, next, it is not with the tools. You see, for designing the chip, they need some softwares. Please try to understand, they need the softwares. So those softwares, there are some companies, they provide only the automation tools like Cadence, Synopsys, Siemens EDA, that is Mentor Graphics. So those all are something which you have to keep this in your mind. Okay, next, it is okay, IDM foundries. Oh, it is moving like this, sorry. IDM, it is taking, okay, IP vendors. Okay, so they will use a reusable design blocks. Okay, like ARM. You might be thinking ARM is a chip manufacturing company. No, it is an IP provider, intellectual property providers like Imagination Technologies, Synopsys, Cadence. These are our IP providers where they can go on reusable their design blocks. So they will produce a block where they can go on keep on reusable. For example, if we have a Cortex M4, that is the family of series, it comes under the architecture V7, ARM V7 architecture. That architecture, that IP will be produced by ARM, and where the companies can go and buy those IP and they can reuse those things. That is what the reusable vendors. Next, outsourced semiconductor assembly and test. So these are the companies where packaging and testing services they will do. So what they will do, no, they will package the things and they will do the test. That is where the companies like ASE, Amcor, JCT, and Spill. So these are the companies which they will do only the what I will tell, the testing service and the packaging stuffs. Okay. Next, we will try to have the manufacturing process of the semiconductor in a high level. See, whatever I am talking is an high level. Each and every step is having its own nuances. Okay, so for you at a time being, you just try to get an overview. Okay, so we have an raw silicon, and that wafer fabrication, it will be moving into it, then the front end processing will be happening, then it moves into back end processing, packaging and testing. I told it in a simple way, but it is a huge process, it is a big process. Okay, sir, your voice is breaking. Now is it clear? Let me. Hello, hello, check. Hello, please confirm me. Someone confirm. Is my voice audible, breaking, or it is coming in continuous way? I'm giving, yes, it's clear. Okay, it's clear. Maybe at some point it might be used. Yes, clear. Okay, thank you guys. So in the fabrication steps itself, you have many things. We want to purify the silicon, and the crystal will be growing, and we want to wafer slicing, we want to slice it, and we want to keep it for oxidation and photolithography and etching and ion implantation, deposition, metallization, chemical mechanical planarization. These comes under the fabrication steps. Now, in the complete IC development process from specification to silicon, first we will try to understand a step-by-step stuffs. Okay, we will try to understand a step-by-step the thing. Okay, first system specification. What no? Suppose you want to design a UART controller for 100 megahertz with low power. We will, let us try to consider an example. Okay, let us try to consider an example. We want to design, okay, we want to design an UART, okay, a UART controller at 100 megahertz with low power. So this is only a design. What they will do, they will create what functional it is want. Okay, it is a UART, that means it need TX and RX. Okay, so it need TX and it need RX, such kind of things. Okay, then their performance. Okay, and they will test for the power budgets and area constraint, operational frequency, interfaces, and the technology node. Everything they will define for this UART. For this UART, they will have a design. They will try to DESIGN. They will try to design it. Okay, that is what you have to understand. Okay, so this is the first step. The first step is only the specification. They will give only the specification for this UART controller 100 megahertz with low power. They will define the functionality, they will define the performance and the power, how much power they can give, and what is the area it want to occupy. Such kind of things they will give only the specifications. Okay, that is what the first thing. Okay, next, it is architectural design. It is high level planning of chip. How no? So for this UART, okay, what are the blocks we have to keep, what are the registers we have to get, and then what is the data path, what is its control logic. You will be having a control registers for this. And what is the memory, suppose if it is having the memory, how it is going to access it, what is the bus interfaces. Those things they are going it in an architecture level. Now they have given only the specification previously. Using that specification, they are building one architecture. They are trying to build one architecture. So they will be having an architecture document and a block diagram, such kind of things. Okay, for example, if you want to do an ALU, okay, so they will give a diagram, they will specify what all the operations it want to do. From the specification, they will go and have some architectural design, and what are the register files, controllers, SRAM, interface logics. These all are something which comes, some examples where you can think of something like an architectural stuffs. Okay, Now comes the RTL design. So now we know a block diagram kind of steps. Now we want to use register transfer level coding. So we want to convert that block diagram into a code part, into an coding part. So here we will use Verilog, system Verilog or VHDL, something like this. So we are going to learn from this part. This is what we are going to do coding from this part, and especially we are going to do coding from the Verilog stuffs. Okay. And the activity is module design, combinational logic, sequential logic, finite state machines. These are the things we are going to do by using the Verilog. Okay. So this is where the RTL design flow. See, sir, what is this? You see, by using AND gate, OR gate, and NOT gate, you can develop your own computer. And how how do you automate in an hardware to have this AND gate, OR gate? We will write a Verilog code for that OR gate, AND gate, and we will try to convert that into the hardware level. Okay, so this is some example Verilog code. Okay, we will give you the, and after the code they will be giving the source file, then they will use compiler, and then they will go and use it. Okay, so that is the idea behind it. Next, functional verification. Once you have written the code, and we want to verify it, okay, whether suppose we have written a design and everything for an AND gate, okay, for an AND gate, we want to test 00 10 11, and we have to test whether it is working properly or not. Okay, and for OR gate and for NOT gate also. So something like this, I'm giving a simple example. So likewise, if an ALU, we have written a code for ALU, and you have to test that. You want to go and test that whether it is working properly or not. So for testing, we have to create a test bench, or by using some simulation, we have to test and giving some assertion and coverage analysis. All those things, these are the methods. So what are the tools? There are models in Questa, VCS, Xylium, Cilium, and then very later, this is open source, we will be using this. Okay, and to ensure that RTL matches the specification, this register transfer logic which is matching those specifications, we will try to understand it. Okay, so this is where the step 4 functional verification, it is happening. Okay, now the logic synthesis. Here, see, in the functional we are able to simulate and we are able to check it. Okay, now we want to convert that into the exact gate level. How to do that? That is where the synthesis part. Okay, simulation is different, that and then synthesis means you are converting that code, that kind of things into something in a gate level, something to the gate level. Here till it is, you are making it, it's something in an, what you can call it as something in a schematic level, you can call this is a schematic level only, but here you are looking in a gate level netlist. Okay, so these all are something we have to go and optimize it. Okay, so for this they are using the Synopsys design compiler, Cadence Genuine, and Yosis is the open source tool that we can go and use for this logic synthesis. See, that logic, you are able to synthesize something according to the hardware level, how you can go and put. Okay, that is this step. Okay, why it is not moving? Design level test, it is taking little bit time. Okay, now it went. Okay, okay, now it is showing. Okay, so next comes the design for test. So it will improve manufacturing ability testing. Okay, by scan chains, boundary scans, MBIST, and JTAG. So it will detect the manufacturing defects. Okay, that is for the design for test. And then floor planning, it is the actual physical stuff. Okay, it is the actual physical stuff. Okay, so physical planning of the blocks. Okay, it is the physical planning of the blocks. And then where the task is, we have to place the macro things and input output pad placements and the power grid planning and the routing channel allocations. Those things we have to, they will be doing in the floor planning. Okay, and here it comes the initial chip layout. Whatever the thing you are trying to do it, okay, that layout you will get after the flooring. Okay, after the flooring you will be getting that uh, layout. Okay, next comes the placement. So you will be having a standard cell. Okay, see, you will be having a cell like structure. Inside that you can have the gates. Okay, so they will go and place these cells. So how to place, we have to optimize this, how the wire length, congestion and the timings, because when the clock pulse, when you're going to give that timing, all the things we have to keep keep in an optimized way. So that is where the step 8 comes in the placement. Okay, that is where the step 8 comes in the placement. Let me check, is there any problem? Okay, you want the material. Okay, I will try to upload it. The next thing, okay, okay, next is clock synthesis, clock tree synthesis. See, we kept something. We have one module, another module, another module, another module. For that, you need to have the clock. You have to distribute the clock to all the modules. So that distribution of the clock properly is done by this clock tree synthesis. So the clock skew rate, how speed it is, what is its delay, and what is the power it is taking. So at the end of the things, we need a balanced clock network. That is what the goal of this ninth step. That is where the uh, goal of this ninth step. Okay. Okay. Routing. So whatever the cells we have been placed, no, we have to route it. We will be having many cells, we have to route. Okay, so the types are global routing and detailed routing. Okay, and it is nothing but the physical interconnection, how the cells, everything is getting interconnected. That is what this step involves in it. Okay, in the step 11, actual physical verification comes by using DRC check, LVC, and ERC checks, and then they will check for the antennas, and then they will go and calibrate the tools like Calibri and Pegasus. That is what the things come from the physical verification. Now in the static timing analysis, okay, they will check. Okay, see, however, whether the, see, for an AND gate, when we try to give input, the output will come, it will take some nanoseconds. Please try to understand. Okay, it is having some delay. So now whenever we try to pass the data inside the inside the what you call the gate level or something like that, we, you need some setup timing. That means the data want to be ready. For that ready, you need some timing. Okay, and then there is something called hold timing. You want to hold the things, so that the data want to be hold, so that the gate can understand this is the input. Next, the path delay, you will be having, it is not only the AND gate, you will be having many gates will be attached. So that path is also will conduct, will give you a delay. And clock uncertainty, there will be some uncertainty in the crystal clocks, so there will, that also will be happening. So we want to check all these stuffs. Okay, so for this they are using prime time, tempest, and open STA. This is an open source tool. Okay, for having the static timing analysis. For the static timing analysis. Next, power analysis, dynamic power, leakage power, IR drop, and EMI analysis. These all are some power analysis stuffs. Okay. Next, the final approval before fabricating. Before fabricating into a chip, the time cleaning. Already we have done DRC, LVS. Now they want to go and clean. Design rule check, layout versus schematics, and power verified, and then signal integrity. They will go and check. Okay, those things. Now the tape out. It is the final GDSA delivery to foundry. Okay, so they will convert all the things, they will be converting into a file format. One is graphics data system to format, the other one is OASIS, Open Artwork System Interchange Standards. Okay, so these are the two primary formats where the industry to store the transfer integrated circuits layout data. So they represent final bridge between the circuit design and actual physical chip. Okay, so still now we are in the software level. Still now we are in the software level. This tape out is the thing which bridges between the fabrication and then the still now what the steps we are looking to know, that design part. Okay, so this what the stuff tape out. This is what the tape out. Now the chip manufacturing at the foundry. Once this file has been sent to the manufacturing for fabrication. Okay, next comes packaging and testing. Final chip preparation, vapor probe, packaging, final test, burn-in, and characterization. So these are the steps involved in it. Okay. Okay, so these are the things I have put that in a graph where you can go on, use and do the stuffs. Okay, so this is whatever the things I explained step by step, I captured is as a flow chart. Okay, now there is something called the metrics in VLSI. There is something called metrics in the VLSI. Okay, so for having a optimized design, PPA, performance, power, area. PPA, they call PPA, performance, power, and area. And there are other metrics, how much yield, reliability, and the cost, thermal behavior, and test coverage. These are some of the other metrics that we want to take care when it comes to the design of this stuff. Okay, so they have some metrics. The performance want to be high, they want to low power and low area, and other metrics like reliability, yield, cost, thermal behavior, and test coverage. Those things they have to go and look into it. Then there are, yesterday itself I told what is this nanometers and everything, no? So how much packed, how much the size of the transistor they can go and pack inside it. That is what this. Okay, so smaller node advantages, high speed, low area, low power, high integration. But the challenge is leakaging, power, process variation, cost increase, complex verification. The leakage will happen. Okay, so because when we reduce the size, there will be a leakage of this transistor. It will go and affect the signal of the other transistors. So that is things when we go low in the, I mean, when the nanometer, I mean the technology comes less. Okay, when we try to reduce to these things, these are the challenges we want to go on take care. Okay, but when we reduces it to these things, these are the advantages we are getting it. Okay, so this is what the role you can go and play in an VLSI. Okay, yesterday itself I have given you, but I thought of giving it to you. Okay, so now the current trend, industry trend, it is AI accelerator, chiplets, 3D IC packaging, RISC-V adaptation. Because why? In the sense, RISC is an open source. Okay, you don't want to have an you don't want to pay a license. You can have their specification, and you can go and make a chip. Okay, and then edge AI hardware, automotive semiconductor growth, advanced packaging, and open source silicon movement. This is what I told. So I will concentrate fully on this open source stuff. Okay, so open source silicon movement is happening. Okay, so the key takeaways, what you have to do in the sense is its specification, design, verification, physical implementation, fabrication, and testing. So there are design companies, there are foundries, there are EDA tools, IP, intellectual property things, packaging industries, and testing industries. Okay, so these are some key takeaways which you have to take from the stuffs. Okay, and these are the commands I planned. Okay, for the next 15 minutes I will try to go and uh, give you some hands-on stuffs where you can go and work. So these are the commands. Maybe you can take a screenshot of this, and I will show you the things. Okay, there is a separate session for the Verilog programming. Okay, for the Verilog programming there is a separate session that we will be on the upcoming sessions. I will be teach you on the Verilog coding also. Now I will try to give you a demo of how to compile the code and how to see the output, such kind of things I will be showing it to you. And then by using the EDA tools also I will be able to I will be showing you the things. Okay, this is what the plan. Okay, okay, so this is what the stuffs I planned to do it. Now let me go for it. In the thing, if you go on type EDA, okay, let me go for Google. Okay, let me go on type EDA playground. Okay, okay, now you are able to see it. Okay, EDA playground, you enter it, go to this first thing, it will be start loading it. Okay, maybe I have already signed in. You can sign in through the the you can sign in through the Google also, I mean the mail ID also. Okay, so now what I'm trying to do is, let me, this is the space where you can go and write the code. Okay, so I'm going to copy and paste the code which have been already written it to you. Already I have written. I will teach you those things when it comes to the appropriate sessions. Okay, before that, let me go and have a cheat of these. Okay, maybe I will take a clock demo. Okay, I will take a clock of demo. Okay, clock demo is there. Let me come and paste it over there. Okay, you right now you don't want to think of these things. Okay, you think there is something. Okay, and then let me try to run directly. Let me try to run there. It is asking, please select a valid tool for simulation, something like that. It started asking. Okay, so let me use for the, in the tools, it is asking here in the left side. Okay, if you see in the left side, okay, I hope my thing is in the left side. If you see in the tools and simulation, if I go here, it is asking to choose the things. I will go and choose this iCar Verilog. Okay, iCar is Verilog. Then here above, any, it is trying to ask if you want to see any waveform or something like that. Okay, let me go and put it. Okay, first I will try to run without this, and I will try to run with that. Okay, so I went and enabled this. Okay, let me run it. Okay, you can see it started running, and my clock signal, I am trying to generate a clock signal, goes from 0 1 0 1 0 1 0. I am able to see that in over here. Okay, I am able to see it over here. in this platform. Okay, I'm able to see the things here. Okay, that is one thing. No, sir, I want to see a simulation tool. Okay, so maybe I will go and enable this. Uh, uh, Wait, sorry. Let me go and enable this open EP wave after run. Okay, I'm going and enabling that, and let me run it again. You see, now it started loading the signal. Let me try to. Okay, now the signal is, you can see that I'm able to see the signal. It run for 0 to 40 seconds, and you see that for every 5 seconds the clock is being ticked. The clock has been ticked. Okay, so now what I did is, okay, I told no, okay, from the uh, this is the code. From the code I am trying to get a signal. I'm trying to convert those things into a gate level stuffs, and all such kind of things I'm able to do with the software. That is what I am trying to insist on you guys. Okay, by using the software where I am able to go and do the things. Okay, that is the idea. Okay, now let me check whether can I upload this document over here, and you guys tell me whether you are able to upload it, and whether you are able to download it or not. Okay, so for that I want to stop the scaring, I mean screen share, and let me try to give the, because they were asking the materials, so let me try to give those material. Okay, so for that give me a second, let me download it, and then convert that into a PDF. Okay, give me a minute time. Okay, I am exporting it. Okay, just a minute, I will upload the things. Okay. Okay, sir, I don't mind share that code in the chat box, sir. Okay, no problem, I will do it. I also don't mind. Good, let me share the code to you. Good, you are interested in the code. Yes, copy, enjoy. I shared the code. Let me try to upload. Okay, and then in the download, what I have, day 2 VLSI select. Okay, hello, I have uploaded the things. Okay, now you check, guys. Are you able to download it? I added it over here, but I don't know whether you guys will be able to download it or not. That you have to check. But the code I have already shared you. Okay, I think it will take a little time. I think so. That's not a problem. Okay, so these are the things. Yesterday also it was showing the things. Okay. No, you are not able to download. Then sorry, pa. You are not able to. I don't know whether you cannot. You will be adding it. Yesterday also I was searching for it, but I didn't get it. Okay, let me features publish attach attachment available right. No attachments available right now. Okay, maybe in the thing attachments. Choose a file. 1 second. Uploading. Upload failed. Okay. Okay. It is something failed. Okay. Maybe they will be sending the things to your mail. I think so. If you request, I think they will be sending the uh, PPT to your mail ID. Okay. So let me share the screen. Okay. Share it. Okay, so this is the online tool. Okay, now let me go on to open my terminal. Let me go on to open my terminal. Okay, and let me check VLSI projects. Okay, projects. Okay, so I have, let me move into the module 1. Okay, so that is what it is happening. Then I already, 1 second, I will pull it back. Okay, I will pull fully back. Okay, so now in this module, okay, I have a file. Okay, this is the command I want to give. Okay, I have the clock demo. I have a clock demo. Okay, and I am going and uh, giving my output file. Okay, let me use the things over here. My output file. Okay, is a clock VV VVP. Okay, very letter P, and I am entering it. So if I try to do that, okay, when I try to do this, at the time of this, it generated a VBP. Let me remove. Already I have done for the demo. So VCD files, you will not be able to see the VCD files, and then remove clock VVP files also. So now you will not be, you can see only clock demo V files only. Okay, so let me clear the screen and let me run the things once again. Okay, and let me check it. Have we got any VV file? You see that clock VVV demo has been created. Once that has been created, I'm going to use VVP command and then clock VVP. Okay, this will create my VCD files, and you are able to see the output 0 1 0 1 0 1. Okay, you are able to see the output for this. You guys create your own thing. Okay, you guys have a communication and try to create the stuffs. Okay, WhatsApp group, and send the link in the chat. Maybe on the tomorrow session I will join in that. That is not a problem. So using this, okay, so now I got that stuff. Okay, then I want to see the what I will tell. I want to go and see the when I try to run this. No, when I try to run, you can see that there is an VCD file. You got an VCD file. If you want to see, if you want to use this wave, GTK wave is an another software utility where you can go and see the waves. You see that I got an wave. Okay, let me enlarge it. I got an wave. Okay, let me do plus plus. Yeah, see, if I click, I'm having a clock. Double click it, the clock will be coming it over here. Okay, so and then control minus control shift plus plus. You can see that. Okay, let me click this and let me run this. Okay, year one, it will show. Okay, let me go at the end. Click. See one. It is moving. Clock. Okay, and it is. So these are the tools. Okay, so if you want to, I recommend you guys to use a local tool, and it will be good by creating projects and all kind of stuffs. But if you guys using EDA tools, it's up to you. Mostly I will try to cover by EDA and this open source, but suppose if something is not possible in the online tool, I will try to convert this in this style. Okay, these kind of intermediate files, changing into these and looking into these things and all, you need a local installation, so you guys will be able to have a better understanding uh, uh, about the code, and you can have more understanding, and you will be getting an industrial knowledge. Okay, that is what I'm trying to tell. Okay, when I try to close the project, it has been went and destroyed. Okay, so now you guys please let me know if you have any doubt. Still 4 minutes left, or else we can wind up the session. I am done with my part. If you have any question and answer, please let me know, or else we can wind it up. Okay, then create a WhatsApp group for PDFs or any other syllabus. Or Udavalli Devi Sri Charan, you please do it yourself, and maybe tomorrow you try to send the link in it. I might be joining it. Okay, okay. Okay, in the yesterday session, I have sent you the, I have shown you the stuffs. Maybe I can show one more time. These are the stuffs which you have to go and use it. Okay, let me open it. Day one. The day one. At the end, I have given the PPT. I asked you guys to take a screenshot of it. Okay. Okay, this is for the Yosis. Okay, maybe you can take a screenshot of this. This is the thing, this is the requirement, and then this is the stuff that you ask how to access the recorder classes, or that you ask the concerned person how you joined, you ask them. These are the things which you have to go and give the commands. Maybe you can take a screenshot. This is the thing, these are the commands, and these stuffs. I think up to this is enough. And the next, if you want to install the open lane, then you have to go and use the Docker stuff. Okay, to go and use the Docker stuff, and then use these commands to install it, and then test for the smoker. Once it has been tested, then this is where the verification, all the things, whether it is installed or not, you can verify by using these things. Okay. Okay, guys. Hope you would have enjoyed the session. I hope so. Okay. Okay, let me stop stop sharing the screen. Okay. So we will see by tomorrow. Okay, with a good hands-on. I will try to make every sessions having some hands-on, so that you guys can go and get an idea about it. Okay. 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 Thank you all. Bye. Any other questions? See, that is what I was trying to tell you guys. Please create a group. Okay. And send the link. Tomorrow chat, in the tomorrow chat, I will join. Okay. Thank you all. Bye.